All right, yeah, welcome everyone to a new edition of the Geometry with Symmetry seminar, and it's my great pleasure today on this new time slot to introduce Changliang Wang from Tongyi University, and he will talk about the linear instability of some families of Einstein metrics. So thanks, Changliang, for joining us.
Yes, thanks for the introduction and thank organizers of the seminar, and especially I would like to thank Amelia Laureate for the invitation that I have a chance to talk this topic here. Okay, so this talk is based on some joint work with Semmelmann and McKenzie Wang. It's about linear stability problem of Einstein metrics. Okay, so let me start by reminding you what Einstein metric being here. We see a Riemannian manifold is Einstein. That means the Ricci curvature is constant. In other words, the Ricci tensor is a constant multiple of a Riemannian metric tensor, and this constant is called Einstein constant. Okay, and so it's some linear stability problem of Einstein metrics will naturally come out from some variational characterization of Einstein metrics. So let's see one of them. Okay, so now let's say we have a smooth compact n-dimensional manifold, and then all Einstein metrics on this manifold are can be realized as a critical point of so-called normalized total scalar curvature function, the S tilde. So here, this is just a volume normalization of Einstein-Hilbert action. It's the integral of a scalar curvature. So, so now we know the first variation of this function vanishes and the Einstein metric. So the natural question is to know kind of the behavior of a second variation of this function and its critical point, an Einstein metric. So that is given here. So let's say now and the Einstein metric G, the second variation of this normalized total scalar curvature function S tilde in H direction. H is a symmetric two tensor here. It's given by a quadratic form. So here, the variation of operate is given by this very complicated expression here. So let me say some words about the notations here. This Laplace star Laplace is just the collection Laplace, and this R circle is just the lateral action of a Riemann curvature tensor on symmetric two tensors by contraction, and this delta sub G is a divergence, and the delta sub G star is just the form of the join of the divergence. And I think all other notations are just standard ones. Okay, so it's not easy. Actually, I think it's impossible to directly see some information like sign of the variation, the second variation from this expression for very general direction H. But the good thing is compact Einstein manifold other than standard sphere, we have a good decomposition for the symmetric two tensors, right? So into three pieces. Okay, so this decomposition is good for this for the study of this variation formula because this decomposition is orthogonal with respect to the second variation of a function S tilde. And so clearly the first, the second, so the symmetric two tensors in the first piece of this decomposition is the kernel of the second variation formula, because that's the symmetric two tensors in the first piece of decomposition is tangent to the orbit of diffeomorphism actions on the action on the Riemannian matrix, and our function is a diffeomorphism invariant. Okay, and for the For the conformal variation directions is in the correspond to the second piece in the decomposition from the classical Ricci-Obata estimate for the Laplace operator, the eigenvalue of Laplace operating on this Einstein manifold. We know it's always non-negative. And then if we look at the second variation along the symmetric two tensors, in the third piece of the decomposition, we'll see Einstein metric is always a center point of the normalized total scalar curvature function. That's because if we restrict the second variation in the trace-free and the divergence-free directions, then the second variation formula will becomes this very simple, has this simple expression. So now we have negative sign in front of this integral, and let's call this operator this variation operator as Einstein operator is collection Laplace minus is 2 R circle. And this is just a constant shift of Ricci Laplace on symmetric two tensors. And this is a second order elliptic operator. And its second order term is a non-negative term. So its spectrum consists of discrete eigenvalues, and almost all of them are non-negative. But because we have this zero order term R circle, so negative eigenvalues are possible, right? So then we say Einstein metric is S2 linearly stable if this Einstein operator is non-negative for the TT tensors. That's just trace-free and divergence-free two tensors. So otherwise, we see as S2 linearly unstable. So geometrically, this restriction for the variation direction, mean onto the trace-free, divergence-free directions, is equivalent to say we restrict the function, the function S2 onto the Riemannian matrix, space of Riemannian matrix with a constant scalar curvature and the fixed volume. Since the tangent space of space of Riemannian matrix with constant scalar curvature and fixed volume are just trace-free and divergence-free symmetric two tensors. Okay. So now let's look at some examples of stable example and unstable examples. So first, some stable examples. The first one is Einstein manifolds with a negative sectional curvature. Okay, so this was proved by Kähler. And also proved by Kähler, we know many compact irreducible symmetric spaces are stable. For example, the standard field, CPN, HPN is a standard matrix. Okay. And also more recently, so 是现者代的小东王国方位 they proved all compact manifolds with non-zero parallel spinors are stable. Okay. And actually, so far, all known examples of compact Ricci flat manifold have non-zero parallel spinor, so they are all stable. And the other proved compact Einstein manifolds with a non-positive scalar curvature and non-zero parallel spin C spinor are stable. Okay. So in particular, this result implies all compact Kähler Einstein manifolds with a non-positive scalar curvature are stable. And here stable means S2 linear stable. Okay, it's about parallel spinor and parallel spin C spinor case. So then Cronk proved complete Riemannian manifolds with imaginary Kähler spinors are stable. Okay, these are Einstein matrix with negative scalar curvature, negative Einstein constant. Okay, so these are some stable examples. Let's say some unstable examples. So first, some symmetric spaces, SPN, module UN. There are two classes, two subclasses of unstable irreducible symmetric spaces. And Jensen's field matrix on this order dimensional on this certain order dimensional spheres. These are just some canonical variation of a standard matrix on the sphere. And also, we have to see for the Kähler-Einstein case, we know compact Kähler-Einstein, if they have long positive scalar curvature, they are stable, right, by one-way result. But for the positive scalar curvature case, if the second byte number is greater than or equal to 2, they are unstable. This is an observation of Cao, Hamilton, and Yeoman. Basically, if second byte number is greater than or equal to 2, we can find harmonic 2 form that's orthogonal to the Kähler form. From that, one can easily get an unstable direction. And also, it's about the Weber product Einstein manifold. If it's a low dimensional, they are unstable. Of course, the compact case, compact. And I think one sort of a trivial unstable example are just the product of the two Einstein manifolds with positive scalar curvature. With of course with the same Einstein constant, is always this kind of product always like unstable. Right. So from these examples, we can see that the Einstein manifolds with long positive scalar curvature are more likely to be stable, right? And for the positive Einstein constant case, the only non-stable examples are just some irreducible symmetric spaces. So, and in the rest of talk, we will just focus on the on this positive scalar curvature case. And so now I think we started this problem, right? Because it naturally comes out from the variation description of Einstein matrix. Right? And I think after Perelman's work about Perelman's proof of Poincare conjecture in study of Ricci flow, we also have some motivation for study of this linear stability problem. You ought to see that there's no kind some functions introduced for Perelman, and that will give us a different variational characterization of Einstein matrix.
Sorry, Changliang.
Yeah.
So before you move on to the functional, so you said there are no known examples of unstable Einstein matrix with negative scalar curvature?
With positive scalar, I mean, okay. The only stable positive scalar curvature Einstein matrix are irreducible symmetries.
All right.
But for the for non-positive scalar curvature case, we have many stable examples.
Stable, yeah, but no unstable.
Yeah, for the positive scalar curvature case, we don't have examples. I mean, stable examples except irreducible symmetric spaces, compact.
Okay.
Can I also say something in between? Just want to
Yeah,
mention,
sure.
I mean, this is of course due to the compactness. So in a non-compact setting, there are more examples. This should be mentioned.
Right.
So for example,
sorry, Trunk, I think he got some non-compact examples, right? The stable.
Right, there are also unstable Ricci flat examples, for instance, in a non-compact system, or there are unstable examples of negative scalar curvature. Yeah. So
okay.
Thanks
just
for the
much richer.
Yeah, that's a
Thank
good
you.
point. Yeah. Okay. So now the first is a so-called W function. Right? It's it depends on Riemannian metric G, smooth function F, and positive scale tau. Right? And then for fixed Riemannian metric G, take infimum for W is a W functional for F and tau, so get so-called a new entropy. And then the isometrics, with positive scalar curvature are critical points of Perelman's new entropy. And of course, shrinking gradient Ricci solidity as a generalization of isometrics with positive scalar curvature are also critical point of this new entropy. So that similarly, we want to know kind of the second variation of this new entropy and isometrics is critical points. That was started by Cao Hamilton and Yeoman, and also later by Cao and Zhu. So from the calculation of second variation of a new entropy, now we see we will still use the decomposition of symmetric two tensors on Einstein manifolds. For the symmetrical two tensors, the tangent to the orbit of diffeomorphism action on Riemann manifold is still is a kernel of a second variation of a new entropy, because this function is also diffeomorphism invariant new entropy. And in the TT tensor direction, the second variation of new entropy is the same as the normalized total scalar curvature function as theta, just up to some positive factor here. And but along the conformal directions, this is different from as theta function. The second variation of new entropy along the conformal changing directions could be negative definite if and only if it's the first non-zero eigenvalue of Laplace function is greater than or equal to twice of Einstein constant. So unlike the normalized total scalar curvature function, so new entropy could have a local maximum and an Einstein metric. Okay. And then we say, sorry, I think I missed some words here, but okay. So then we say a closed Einstein manifold with Einstein constant, with positive Einstein constant is a new stable if it's a local maximizer of the new entropy, and it's a new linearly stable if the second variation of the new entropy and its Einstein metric is less than or equal to 0. So from this the second variation behavior of the new entropy and Einstein metric, we just looked at in the previous slides. We see if Einstein metric with positive scalar curvature is a new linearly stable if and only if two conditions. The first one means it's S2 linearly stable, and second condition is the first non-zero eigenvalue of a Laplace operator on functions, on smooth functions, is greater than or equal to twice of Einstein constant. So the new linearly stability is stronger than then S2 linearly stable. So, but these two kind of stability notions are closely related to each other. So now we look at the relationship between the linear stability notions and the dynamic stability of a rich flow and isometric. So Riemannian matrix, maybe up to diffeomorphism and scaling. The isometrics are fixed point of normalized, maybe normalized rich flow, right? So up to diffeomorphism and scalings. For the rich flat matrix, just a fixed point of this rich flow equation up to diffeomorphism and scaling. But for the isometrics with non-zero scalar curvature, we need to modify this rich flow equation by adding some multiple of metric on the right-hand side of the equation. Then here we see our instant metric is dynamic stable if it is stable as a fixed point of this rich flow dynamic system. Right? That means the normalized rich flow starting and a Riemannian metric that's very close to the Einstein metric that exists for all time and will go to Einstein metric close to the given Einstein metric. And then Crank's work, we know is Einstein metric with positive scalar curvature is dynamically stable if and only if that's new stable. Right. So in particular, we see S2 linearly unstable implies new linearly unstable. This implies to new unstable loss, right? And it's equivalent to. So so we see if Einstein metric is dynamically unstable, right? That means if we start the rich flow or normalized rich flow from a metric very close to that, or just a small perturbation of the go away from this this unstable Einstein metric, right? That will not appear in the long-term limit of the rich flow. So in some sense, we can ignore this unstable Einstein matrix. So we want to determine which Einstein matrices are stable or unstable within the study of rich flow. So now we will focus on a special and very important class of Einstein matrix. It's Riemann manifolds with real Kähler spinors. So we want to look at the stability of this special Einstein matrix. So for that, let's first recall what the Kähler spinor means. So a spinor is a section of spinor bundle is complex vector bundle, right? And a spinor is called a Kähler spinor. It's Kähler constant mu. If this differential equation is satisfied for all vector field x on the manifold, it's a dot means Clifton multiplication of the vector field of the spinors. And okay, so of course, if me,
is it just me? I'm still seeing the dynamical stability slide. I don't know if it's just
sure.
my connection.
Same with me.
Yeah.
Yeah. Okay. Now I can.
Yeah, still the same. There you are. Yeah.
Okay.
There is the Kähler spinors. Okay.
Oh, okay. Sorry. Yeah. Okay, so
sorry.
okay, no. So now if it's a Kinney constant, if we allow the Kinney constant to be 0, then we got Perelman spin. Right? So this is a case that one we studied, and so for manifolds with a Kinney spinor, we have the Ricci curvature has this expression that will be 4 mu square times a minus 1 times Riemannian G. So the mu square has to be real number. Right? So the mu can only be purely imaginary or real. And then we call a non-zero Kinney spinor as a real or imaginary, depending on the Kinney constant is real or purely imaginary. These two kind of Kinney spinors and on non-manifolds are very different. And I already mentioned that the Cronk proved that the complete Riemannian manifolds with imaginary Kinney spinors are stable. Right? They are Einstein manifolds with negative scalar curvatures, negative Einstein constant. So so now we want to study the stability of manifolds with real Kinney spinors. They are Einstein manifolds with a positive scalar curvature, positive Einstein constant. So by a series of work by Friedrich Hijazi and also Bell, they got some this very rough classification of Riemannian manifolds with real Kinney spinors. They could be actually in the even dimensional case, if the dimension is not 6, they can only be round sphere. And in 6th dimension, they are so-called straight nearly Kähler manifold. And in all dimension, they could be they are Sasaki-Einstein, and in the 7th dimension case, they are nearly parallel G2 manifold, including Sasaki-Einstein and 3 Sasaki and so-called proper nearly parallel G2. That's so now we know round sphere, the standard sphere, they are stable, right? So so then we need to study the stability of Sasaki-Einstein and the straight nearly Kähler in 6th dimensional and also in 7th dimensional nearly parallel G2 manifold. That's because the definition of these notions. So almost a Hermitian manifold is called straight nearly Kähler if this equation satisfied, means it's just a Laplace of the covariant derivative of this almost complex structure is a sort of antisymmetric. And so of course this notion is nearly Kähler could be defined for all even dimension. But in 6th dimension is special. There will be Einstein and actually admit a real Kinney spinor. And this nearly Kähler 6 manifold also have some SU3 structure. And now, as in the 7th dimension case, they are got a nearly parallel G2 manifold. So here, a Riemannian manifold is called nearly parallel G2 if it emits 3 form. The whose stabilizer and each point is asymmetric to the Lie group G2. And we also have different equations. So how to start of d of this 3 form equal to 8 times some constant times this 3 form. And if we further call nearly parallel G2 is proper if if this Riemann manifold does not have a Sasaki-Einstein structure. Okay, so then for the Sasaki-Einstein, let me very briefly, quickly recall the definition. We know a manifold is called Sasaki. It means its metric cone is Kähler. This is one way to define Sasaki manifold. Of course, there are many different equivalent definition of Sasaki manifold. I want to mention another one. Here in this definition, Sasaki manifold means we have a Kähler vector field that has unit length, and this Riemann curvature tensor satisfies a certain equation here. And this vector field, this Kähler vector field, C is usually called the Riemann vector field, and we see a Sasaki manifold is regular if this Riemann vector field is a regular vector field. It means its integral curves are closed, and actually it induces a free S1 action on the manifold. Basically, there will be a circle bundle over a Kähler manifold, and a Sasaki-Einstein manifold is just a manifold for Sasaki and Einstein. And the Einstein constant for Sasaki-Einstein manifold, the Einstein constant must be n-1 in the dimension of the manifold. Now, our main result for the stability problem of this manifold is here. So actually we can show these manifolds are S-tilde linearly unstable. The first is a Sasaki-Einstein manifold with a second byte number greater than 0. Or in 6-dimensional, the strict nearly Kähler 6 manifold with second or third byte number greater than 0. And also in 7-dimensional case, the nearly, okay, sorry, I think here I mean nearly parallel G2 manifold with a third byte number greater than or equal to 0. Okay. So basically we can use harmonic forms of these manifolds to get some destabilized direction. So as a corollary, we have this kind of rigidity result. So yeah,
we are having a big delay with your screen, and maybe I suggest you turn off your camera, because I guess your connection is unstable.
Oh, okay, sorry. So okay, yeah, I will move that quicker than what I see. So now can you see which page you can see now? You see the
we are seeing your theorem
from Harmonic. Sorry, our theorem. Okay.
Yes.
Yeah. Can you see the corollary? Oh, okay. Okay. Yeah. So now if for the S-tilde linear stable complete simply collected strictly nearly Kähler 6 manifold and nearly parallel G2 7 manifold, they are rational homology sphere. Okay. So now let me see some words about the proof. Can you see the next page now? Okay. So for the nearly parallel G2, okay,
we cannot see it. Could you please turn off your camera? I guess the connection is going to be better. I will turn off your camera.
Let me see.
Changliang, I will turn off your camera.
Okay, sure.
Okay,
yeah,
okay.
I'm doing that. Okay. So
okay,
now
okay,
is that better? Okay. So now our nearly parallel G2 manifold, we have these decompositions for the 2-form, 3-form, and symmetric 2 tensors as irreducible G2 representations, and then we can show the harmonic form, the harmonic two forms has to be in this. Okay, so in the decompositions, this indices denotes the dimension of spaces. So the harmonic two forms has to be in this 14-dimensional piece, and for the harmonic three form has to be in this 27-dimensional piece. Okay. And then for example, for the from the harmonic three forms, we can see is in the symmetric decomposition of symmetric two tensors. We also have a 27-dimensional piece, and actually this S2 27 and lambda 3 27, between them there's a linear isomorphism. So then from the harmonic two form we can get a symmetric two tensor that's trace free, and actually we can also check that the divergence free, and from that we will actually that from that we will get a distance another direction. It's about the G2 the G2 manifold, G2 case. Okay, so now let's move to the homogeneous ones. Homogeneous ones. So we know that it's joint work with McKenzie. About 2 years ago, we see the only new stable simply collected homogeneous strictly nearly kinetic manifold is a standard sphere. This is based on the kind of classification result for the homogeneous strictly nearly kinetic manifold. Actually, we only have 4 of them. So here we basically we check that case by case. Yeah, we only need to check 3 of them. So as long as sphere is stable, is well known. Okay, but here we need to use new entropy, since I think for at least one of them we got instability from the conform variation directions. And for homogeneous nearly parallel G2, they are also classified by Friedrichs, Manifolds, and Semmelmann. Yeah. So we have 3 subclasses. So here first is just a single one, so Jensen sphere metric. We know that's S2 linearly unstable. So it's unstable. And we have in the second class we have infinite many examples. Isometrics Aloff-Wallach spaces. SU3 module circle. The circle is embedded into SU3 in this way. Okay. And also a third one is just a single example is Boucher space. And now in the for the Aloff-Wallach spaces by some works started by McKenzie Wang, we know for each Aloff-Wallach space there are exactly 2 Einstein metrics, and I think almost all of them are nearly parallel G2 manifold. Okay. So, but anyway, we can show all these invariant Einstein metrics on Aloff-Wallach spaces are still linearly unstable. And in joint work with also your Semmelmann, we can also show that the nearly parallel G2 metric on Boucher space is also S2 linearly unstable. It's homogeneous cases, and for the Sasaki-Einstein ones, there's no kind of regular, especially the regular Sasaki-Einstein manifold. You know, they are just one S1 circle over kind of Einstein manifold. So now we have 2 Einstein manifolds on the total space is Sasaki-Einstein, and on the basis kind of Einstein. Right? So naturally we can look at the relationship between the Einstein operators on these two Einstein manifolds, total space and base space, and then we can get a very explicit expression between them. And from this we can easily see that if the base Kähler Einstein manifold is negative, and actually it have the Einstein operator has a eigenvalue that's less than -8, then the total Sasaki-Einstein metric is unstable. And also we can show that if the base Kähler manifold has second band number is greater than or equal to 2, the total Sasaki-Einstein manifold is also unstable. It's S2 linearly unstable, and that is item 2 here. Maybe it's cannot appear. Okay. Oh, it's here. Okay. So and then for the regular Sasaki-Einstein, now we only need to look at the case whose base has whose base Kähler-Einstein has second band number equal to 1. Of course, the Hermitian symmetric, irreducible Hermitian symmetric species are this kind of Kähler-Einstein manifold. So we look at the Sasaki-Einstein, regular Sasaki-Einstein manifolds over this special Kähler-Einstein manifold, stability of them, and we can check almost like all this kind of regular Sasaki-Einstein. I mean, over Hermitian symmetric spaces are unstable. It's S2 linearly unstable. And then finally, I want to mention that from our previous work I mentioned earlier, for the homogeneous cases, we can conclude that so it's a low dimensional. I mean, if the low dimensional homogeneous Einstein manifolds are almost all unstable. I mean, now with of course positive Einstein constant case. So for the dimension less than or equal to 7, we can determine all of them except only one manifold is S3 times S3. I think that's all I want to say.
Thank you, Changliang.
Okay, thanks.
Feel free to turn back on your camera if you want. Are there any questions for the speaker? Comments?
I have.
Sorry.
So
Okay.
on this previous slide, where it said new unstable from conformal variations, does you mean that you discovered a small eigenvalue of the Laplacian? What do you mean by that?
For which one?
You wrote a statement like these manifolds are new linearly unstable from conformal perturbations.
No, actually,
which sense conformal?
For only some of them. I mean, of course, S2 okay, so S2 linearly unstable implies new linear unstable automatically. For some of them, you mean this slide, this page?
Yeah, this slide. This statement is say it's the new unstability from conformal variations. Do you mean like you do conformal perturbation? So do you mean you discovered a small eigenvalue?
Yeah. Maybe for some of them. But not all of them.
What do you mean? I mean,
it's I mean, your question is about this page, right? This the regular Sasaki-Einstein.
Yeah, I found the statement a bit confusing when I read.
I think for
okay, the 1, 2, 3.
Oh, well, yeah, 1, 2, 3.
They are conformally unstable, so they have small eigenvalues. That's what they're saying. But the others are properly I mean, like, okay, yeah, now I think now it makes sense. Yeah, thank you for showing the slide again. And maybe I also have another one. I mean, you're basically talking about instability criterions for Einstein manifolds. Do you see any? I mean, it's much harder to prove stability than instability. Do you see any chance to establish a method to check also the stability of some positive Einstein manifolds? Do you see any candidates that could be stable where it's not known up to now?
I don't have a good idea for showing the stability of Einstein matrix with positive scalar. I think, yeah, in general, maybe we need some Weisenberg formula. But yeah, for the manifolds with real Kähler spinors, maybe standard spheres are the only stable ones, maybe. Yes. But
Okay.
yeah, in general, I should say I don't have a good idea. Yeah, to get some good criteria for stability of Einstein manifolds with positive scalar.
Yeah, I mean, it's much harder to prove that the property is positive than just finding a negative.
Yeah, that's harder.
Yeah, okay, thank you.
Other questions? Well, if it's not the case, then let's thank Changliang again for a nice talk.
Thanks. Thank you for your attention.